really should be able to balance them. If you can't balance them, then that might be an issue on the exam because I might ask you to balance them as part of your grade. So if you're still struggling with balancing equations, I really suggest that you get some tutoring help. You know that we have a student tutor. We also have tutor.com. So you can get tutoring help sort of like 24/7 from them as well. And just like showing them things like this to help you in practicing balancing is important. So this was really the first kind of like identifying kinds of reactions. Synthesis, decomposition, you can identify they're the opposite of each other. Synthesis is building more reactants, fewer products. Decomposition is the opposite, more products, fewer reactants. Single displacement, double displacement, remember, is where there's an exchange. So there's a swapping of chemical partners. If it's an element in a compound, it's single displacement. If it's two compounds, then it's double displacement. So looking at the first one, what is that? Synthesis, decomposition, single or double? It's a single displacement. Single displacement because there's an element in a compound. So do you see how basically the hydrogen is getting swapped? The hydrogen goes from being with the water and now it's over with the hydrogen or with the chlorine, sorry. So if you see an element in a compound and there's just two of each, then you know that it's a single displacement. What about the next one? So this one, notice you have water breaking down into hydrogen and oxygen, so that's forming more products. So this is that decomposition reaction. CuO plus H2 makes H2O and Cu. Single displacement. Element in a compound again, making a different element in a compound. So if there's like same number on reactant and product side, then you know that it's an exchange. So that's either a single or a double. So the next one, the magnesium hydroxide would be, that one is it's not a single because do you see that those are two compounds? So we have magnesium and the hydroxide. We have hydrogen and the chlorine. So we have two compounds making two different compounds. So in that case, it's a double. Okay, so if two compounds or reactants making two different compounds as products, that's a double. Whereas if it's a element in a compound swapping a single pair, then that's the single. What about KMNO4? What is that one? Find the arrow, count how many reactants, how many products. If they're equal, you know it's an exchange, but this isn't, so you know this is one reactant, three products. This is a decomposition. What about NaHCO3? That's a decomposition as well. One reactant, three products. So just think it means like things are breaking down. So we're going to get more products out. Zn plus HCl makes H2 and ZnCl2. Two reactants, two products, so you know it's an exchange. One of them is an element, one is a compound, so that makes this a single displacement. Sn plus Cl2 makes SnCl4. That's a synthesis. Synthesis because I have two reactants, only one product, so I'm building things. H2SO4 plus NaOH making Na2SO4 and H2O. How many reactants, how many products? Two of each. You know it's an exchange. So this is a single or a double. This is a double. And then so is the last one. So the last one, NiNO32 plus NaOH. So I have two reactants making NiOH2 and NaNO3. So I have two making two, so I know it's a displacement type. Two compounds making two different compounds, so this is that double. So I suggest that you go back over one, make sure you can balance these. Two, go back over and practice them. And I will tell you again, remember that the blank PowerPoints are in Moodle. Those are like the PowerPoints for printing. There's no notes on them at all. If you don't have these, you can actually open my marked up PowerPoint, which will be this, so that you could go through and practice them and then check your answers so that you can actually see, okay, do I actually understand this? Do I have this down, or is this something that I still need to go back through? So I gave you a quarter page. tried to make them kind of small. Okay, so you'll get this on your exam. Okay, so on your exam, you'll get this little handout. So on this little handout, do you see the first four? So the first four are really just descriptions of what is synthesis, what is decomposition, what is a single, what is a double, just to help you in identification. Then we went on and we talked about combustion reactions, right? So we talked about combustion is any kind of fuel plus oxygen makes carbon dioxide and water. So you see that as the list. So it really doesn't matter if it's CH4, C2H6, you could have C8H12, so you could have any number of fuel molecules. And remember, fuels are hydrocarbons. So having any kind of fuel, remember that this is always the fuel, any kind of fuel plus oxygen, breaking that fuel down into carbon dioxide and water, that is a combustion reaction. So it doesn't matter if I put water and then carbon dioxide or carbon dioxide and water. If water and carbon dioxide are the products, then you know it's a combustion reaction. And we talked a little bit about what happens if you have incomplete combustion. Remember, that's if there's not enough oxygen, how you can develop soot, which can cause a chimney fire, how you can create carbon monoxide, which is an odorless, colorless gas that ends up binding to red blood cells and blocks oxygen binding, so people suffocate over time. So remember, we talked about that before. Then we went on, we started talking about oxidation reduction, which is like the next little group of things that I've got on your little handout. So remember, in identification, things are oxidized if they gain oxygen, right? So if something is just an element and now it's an element with oxygen, then that means it gets oxidized. So if you look at a reaction and something increases in the amount of oxygen that it has, that is oxidation. And so that combustion reaction is a good example. Fuels get oxidized. If they lose electrons, which is what happens when metals form cations, when metals form ionic bonds, that's also oxidation. Or if you lose hydrogen. So the example that we went through is we talked about alcohol detoxification, how your liver cells detoxify alcohol into acetaldehyde. Then if you look, so you see that's listed under your oxidation part. So it's any of these, but if oxidation happens, so does reduction, okay? So if something is going to gain oxygen, something's gonna lose oxygen. So in the reaction, there's like a swapping of oxygen, or there is a swapping of electrons, or there is a swapping of hydrogen. It's gonna be one of those three. So losing oxygen, reduction. Gaining electrons, like those nonmetals, that is reduction. And if hydrogen amount goes up, increase in hydrogen content, that's also reduction as well. So you see those? I gave you kind of like little examples for them on ways like what are things that you can look for to pick that out. Then we went through some of the examples, okay? How ionic compounds are oxidation reduction, how combustion is oxidation reduction, single displacement reactions where you have an element in a compound and there's a swapping of oxygen or a swapping of hydrogen. Both of those are examples of oxidation reduction. So I am not going to ask you to like complete a reaction. Like I'm not going to give you the reactants and go, tell me what the products are. No, all right? So what I am going to do though is I am going to give you something like that top one. So, and say what gets oxidized and what gets reduced in this reaction. So you need to be able to look at the reaction, you look at what the reactants are, and then look at what happens in the reaction. So you kind of have to look at V and then see what happens to V once it becomes a product. So you have to compare vanadium, which is V. You don't even need to know that, but you need to compare the V. You look, you see that V is a metal and oxygen's a nonmetal. So as soon as you see that, you go, oh, that's an ionic compound that's formed. So if I'm forming an ionic compound, then I know the metal gets oxidized and nonmetal gets reduced. And that's actually even on your little sheet there. All right, then the next one. So the next one, if you see it's a combustion reaction, and this is why you need to be able to recognize these reactions. A combustion reaction, the fuel, which is the carbon-containing reactant, is always oxidized, and oxygen's always reduced. And then for those last two are single displacement reactions where I have an element in a compound swapping one partner. Well, in the first one, the partner that's getting swapped is oxygen. Do you see that iron loses its oxygen? So iron goes from Fe3O4 just to Fe. So you need to look and see, okay, well, what happens to that reactant when it becomes a product? Same thing with the hydrogen. Hydrogen ends up as H2O. So I see that hydrogen gained oxygen, which means it's oxidized, and Fe3O4 loses its oxygen, which means it's reduced. And then the last one. So the last one is, again, a single displacement where it's swapping hydrogen. So when you start off, see how Br2 all by itself, but on the product side, Br2 now has a hydrogen. So Br gained hydrogen, which means that it's reduced. And then if you look at NH3 and you follow to look at nitrogen on the product side, you see that it loses its hydrogen. That's why it's oxidized. Okay, so I encourage you to practice those. Here's some other ones to practice. I will fill those ones out as well. Maybe if we get time, it depends on how this lecture goes in Thursday's lecture. We may go back and try to do more of those, but try these. All of these are oxidation reduction reactions, okay? And I'm not going to give you a reaction that's not. So if I ask you what gets oxidized, what gets reduced, it's going to be an oxidation reduction reaction. Then we went on and started talking about, well, what are common organic reactions that you're going to see over and over and over again for the rest of the semester? And so this pair is one of the most common. Condensation reactions is how you put things together. So if you have a lot of small pieces and you need to build them, they get linked together by removing water. So think of condensation. Condensation is always going to have water as a product. Condensation is always taking molecules and putting them together. So if you sort of track from left to right, two smaller molecules end up being joined into one larger one. Whereas the opposite reaction, because this is a reversible reaction, the opposite reaction is what happens if you have big molecules and you need to break them down, like what happens in digestion. So when you eat protein, you cannot absorb protein into your blood. It's too big. It has to get broken down into its smallest building blocks, which are amino acids. And so hydrolysis is what does that. So hydrolysis breaks molecules into smaller and smaller pieces, and it does it by adding water. So remember, hydrolysis, water is going to be a reactant in hydrolysis, and it'll look like molecules go from being one larger piece to two smaller pieces. Then we started talking about fats, and that's kind of where we've stopped. So we were talking about this is the first nutrient molecule. Yes, this actually is covered in chapter 4, but they cover half of it in chapter 4, half of it in chapter 5. Not a big fan of that, so I would much rather have all material for each of the nutrient types covered in one chapter. So in this, I just moved everything over. So lipids are really the true category of fats and oils. And the characterization of all lipids is that they're long chains of carbon, so they don't mix with water, right? So they're a lot like all of the fuels. They separate, they're nonpolar in their nature. If they're saturated, then they're all single bonds. And then remember, we are looking at these. So these are those saturated fatty acids with some examples of where you find them. Then we looked at some of the unsaturated. Unsaturated just means that it has one or more double bond. If they call it monounsaturated, there's only one. If there's more than one, then it's polyunsaturated, and it might have 2, 3, or even 4 double bonds. Notice those double bonds, their orientation or the way that they look, it's always like this, right? So see how that double bond always has the groups extending up the same direction? So remember that those are all cis. So what cis double bonds do, though, is they create a bend. They create a bend in the molecule. And so I have in my little, like this little picture sort of right here. This is an example of what happens if you have a couple of fatty acids with that cis double bond. It creates a bend. So there's 2 of them. So it's just sort of like that double bond creates these angles that go out. And so remember, this means that molecules can't fit in tightly together. But if they're saturated, if they're all single bonds like this, then you can arrange the zigzag so it's in a nice alignment. Saturated fatty acids, they can pack in tightly together, the ones that have all single bonds. they can pack in tightly together and become solid at room temperature. So that's why like bacon grease, meat drippings, okay, like lard, all of those things are solid at room temperature because they have a higher percent of saturated fatty acids than unsaturated. So I made the analogy like, I always think of saturated fatty acids are like knives in a drawer, right? So take knives out of the dishwasher, you put them in the drawer and they all just lay there, right? Unless you have really weird looking knives. But most knives are just sort of like straight, no bends in them, and they all line in there nice and tight. Remember, to become a solid, you have to get really close. Molecules have to get very close together to become a solid. So the reason that these can be animal fats are typically solid at room temperature is because they contain a large number of saturated fatty acids. Plants, though, they make a lot of unsaturated fatty acids. So like olive oil, canola oil. And so having the bend, I always think of them, they're more like forks, right? So if you pull forks out of the dishwasher and you throw them in the drawer, you know how they always stick up? They don't like line flat unless you're one of those OCD people that like has to put them all exactly in an order. That's not me, okay? But they never like fit down like snug in the drawer because the tines of the fork, some go this way, some go that way. So they can't pack in. That's why they stay liquid at room temperature, because that cis double bond creates a bend. Polyunsaturated are even more so because a polyunsaturated is going to have a bend at every cis double bond. So that one will end up almost looking kind of like a U before it's all said and done. The molecule will end up with like a double bend in it, and that'll keep it from being able to be a solid at room temperature. So one of the reactions that they use to be able to take unsaturated fatty acids and convert them into saturated fatty acids is by a process that they call hydrogenation. So hydrogenation is exactly that, adding hydrogen. So do you see hydrogen in the name? Okay, so the way you can identify hydrogenation, and some people say hydrogenation, that's fine. It's hydrogenation, but however you want to pronounce it so that you can remember it. Hydrogenation is when you add hydrogen, breaking the double bond, converting it to a single bond. So in hydrogenation, you will always see hydrogen is a reactant, and the double bond becomes a single bond. So that is how you can recognize a reaction where hydrogenation occurs. So during the 1950s, hydrogenation of oil was actually used to develop margarine and Crisco. Okay, so if you've ever had Crisco, Crisco is like this white shortening. It's a solid at room temperature. Well, Crisco is vegetable oil. Started off as a liquid. So that top fatty acid that's up here, this is what your vegetable oils contain to high amounts. Remember that if it's got a double bond, it's got a bend. If it's got a bend, it's going to be liquid at room temperature. So what they do is they add hydrogen in the presence of a catalyst, and that hydrogen then breaks the double bond. So it converts this unsaturated, monounsaturated fatty acid and converts it into a saturated fatty acid so that the bottom, see that it's now all just single bonds, and this can pack in tightly. The benefit, the reason that they did this is they said, oh, this is a whole lot more spreadable. So that's the benefit. If you've ever taken cold butter out of the refrigerator and tried to like spread it on your bread, it like tears your bread all to pieces. Okay, that's why most people don't put butter in the refrigerator. They just leave it out because when it's cold, it's really hard. Margarine and Crisco, they don't have that characteristic. Also, oils, like how old is the vegetable oil in your cabinet? Do you remember how long ago you bought it? Mine's like 3 or 4 years old, I would assume, right? Because it has a super long shelf life. So oils last a long time, but butter doesn't. So the next time that you go to the grocery store, pick up a package of like Blue Bonnet and look at its expiration date, usually 9 months, okay? Pick up a package of butter, it's about 2 months. So much longer shelf life. And doing this reaction really wasn't difficult and it actually got rid of a lot of oil that they had left over from World War II, and so it was a pretty low cost. So they had the materials already there. So if you've ever tasted Crisco, Crisco tastes like nothing, right? So Crisco is just sort of like this grease, but it doesn't have anything else in it. So they typically add like butter flavoring. I can't believe it's not butter flavoring. So they add stuff like that to it to give it more of a butter flavor. But the last way that they kind of got everybody to buy into this is they said it's healthier because it's not from an animal product. So this is a vegetable product that we have hydrogenated. It is more healthy for you because it does not contain cholesterol, which butter does, because butter is an animal product. Butter is made from cream from a cow. And so it does have cholesterol in it. So these were all sort of the things that they pushed in the 1960s. And in fact, there was a period of time where people were like, oh, I don't use butter. No, that's not healthy. I use margarine instead. Okay? The problem is when they hydrogenate, when they add hydrogen to break the double bond, about 99% of the time, it happens like normal, like you would expect. But about 1% of the time, so remember you got that cis double bond, so the double bond you're trying to break. So you break this double bond, but a small percentage of the time it reforms. And when it reforms, it doesn't reform as a cis double bond, it reforms as a trans double bond. So do you see that difference? So again, you got to think back to chapter 4 because we talked about cis and trans, one of the reasons we talked about it. So you can see the difference between the cis. Remember, that's the double bond, and both of the groups point up or point down. But trans, they point out on opposite directions. So then they started doing more studies about, well, what are these trans double bonds? There is no naturally known enzyme that can break a trans double bond. So if you're ingesting food that contains a trans fat, when you go to break this down, you get to that double bond, it stops. Because there's no enzyme. Remember how enzyme shapes are very specific? Enzymes that break cis bonds cannot break trans. So then they started doing more research. Okay, well, somebody that eats a lot of these hydrogenated fats, what kind of health challenges are you seeing? And they started to see that having a diet high in trans fats increased your circulating triglycerides, which are your fats in your bloodstream, increasing what they call the bad cholesterol, which is your LDL, decreasing good cholesterol, and those together increase your risk of heart disease. So I will tell you that in Europe, this was determined in the early 2000s, and trans fats were banned by 2005. We're a little bit behind. And a lot of it has to do with food manufacturers because they had gotten all of these recipes, the ways that they made all of our convenience foods, they all contain trans fats. So cookies, crackers, it increased their shelf life because remember we said Crisco and margarine, they last a whole lot longer. If you're going to use butter in a cookie, then it's going to go bad sooner. It's going to get stale. But if you can use Crisco, then it's a much longer shelf life. So there was lots of this well, we have to redo the recipes for them. Some people said in the 2015s, they were oh, well, Oreos just don't taste the same as they used to. And it's because of those changes that occurred. And by May of 2019, it was really supposed to happen in 2010. It got pushed back about 9 years before it finally happened. But in May of 2019, no trans fats are in any kind of prepackaged foods. So when you think about prepackaged foods, and I can try to do this, but it's not very happy about it. Magnify slide. Okay, so if you look, what do you see? What do you see, things that you eat? Cake. You know, the Pepperidge Farm already made cakes, the freezer cakes. Okay, cakes. Frosting, anyone? Frozen pizza, anyone? Popcorn, microwave popcorn. Those little biscuits in the tube. Okay, so you look at them and you're oh yeah, yep, I eat that, yeah. So all of these kinds of foods, they all had to be modified in order to take and change the type of fat that was used, the type of lipid that was used in the recipe, and still try to maintain the flavor of it. So now, if you buy margarine now, it doesn't have trans fats. They have to do a couple of extra steps in the hydrogenation process to make sure that no trans fats are produced when making margarine or Crisco, but it doesn't have it anymore.
Does that mean that, like, in the grocery store you have trans fats in it?
No, nothing in the grocery store. So then if you Google, like, where are trans fats in our Americans' diet? So if you take an oil and you heat it for prolonged periods of time, it can also hydrogenate it, okay? So where do you think of grease that is in a fryer that is on for 20 hours a day? Fast food restaurants. So now, really the only place that you get trans fats, yes, unfortunately, is from your Chick-fil-A, is all from fried French fries. All because in order to fry, they've got like fryers that stay hot all day long. And so that high temperature can actually cause random trans fat formation, but that's really like kind of, so think about that. You're like, maybe I should have that grilled instead of fried, but that's really like the one place that it's still in our diet. But it was a greater like reduction in terms of the amount of trans fats that people were eating. And unfortunately, a lot of these prepackaged convenience foods, like these are foods that people with like lower economic availability, this is what they eat because it's easy, because they don't have the time, they don't have the ability to like make things from scratch, that type of stuff. So it's something that's quick. And so that it ends up affecting that kind of group more than it would other people. But it is a plus that it's now, that's changed, okay? The last one. So in this, you can see hydrogenation, okay? So way you can identify hydrogenation is when you add hydrogen to a double bond and convert it to a single bond. So you see that on your little cheat sheet. So like I said, you'll have this. You get this on the exam. So you don't have to worry about like copying this onto your note card because I'm going to give you this. I'll make it a little bit bigger just so it's a little easier for people to see. But this will be on, you'll have this when you come in and take your test next Tuesday. So just remember, last one. So the last one is the last way to be able to break a double bond. And instead of adding hydrogen, we're going to add water. So because of that, they call it hydration. So sometimes people get hydration and hydrolysis mixed up because they both sound kind of like water. So what you want to remember is that hydration is when you break the double bond by adding water to it. So when you add water, hydrogen gets added to one of the carbons, alcohol group gets added to the other carbon. So it'll always form an alcohol group. Remember, that's the OH. And again, I'll also give you the functional group, whether you need it or not. I'll give you the functional group handout. Since I gave it to you starting last time, you'll have it there if you need to refer to it anytime through an exam. Okay? So in this, you might have a really long chain. It could be a polyunsaturated, but if you do hydration, you're going to see the double bond become single bonds, and you'll have a hydrogen added to one of the carbons and alcohol added to the other. So let's do some practicing. I am not going to ask you to finish any reactions, okay? I'm just going to ask you, what reaction is this? So if you look at this first one, what reaction is this? So look at your page. Yep. So this is hydration. I'm taking the double bond, the carbon with the double bond. See how on the product side it's a single? So I've broken the double bond and I'm adding water. So I end up with a hydrogen on one of those carbons and alcohol group on the other. What's the next one? Hydrogenation is fine to say it that way. Hydrogenation. And you can tell this because you're adding hydrogen. If hydrogen is a reactant, H2 is a reactant, double bond is converted to a single bond, that's hydrogenation. What about the next one? So now do you see when you look at this, do you see that you're not breaking a double bond? Right? So you know it can't be hydrogenation or hydration. So it is where water is a reactant. It's hydrolysis. Okay, and if you look there and there, those are the same. And here and here, those are the same. So what I did is I took this big molecule and I split it into two. I added a hydrogen to one side, an alcohol group onto the other side to be able to break the molecule, a big molecule broken into two. But you can tell this one, you don't see a double bond. Two, you see that water is a reactant. So that's another sort of way to be able to differentiate between the two. So what's the last one? This is, so I'm adding what? So you see a double bond becomes a single bond. Am I adding hydrogen or water?
No, water.
So if it's water, then this is hydration. So this is the same as that top one. So see the double bond plus water forms, breaks the double bond, making that alcohol group. Okay, so we have a couple more practicing ones. We will do these ones next time. Go through, practice those yourself. So look, I did like I said, you're not gonna have to finish a reaction, but you should be able to look at the reaction, given the total reaction, and pick out what happened in the reaction. So this brings us into the next nutrient. Okay, so we've covered like lipids in this chapter, in chapter 5. So in chapter 6, entire thing of chapter 6 is all about carbohydrates. So the goal today is to try and get as far into those monosaccharides as I can. So when you see the word carbohydrate, this is referring to carbon and water. And they named these carbohydrates because the ratio of carbon to hydrogen to oxygen is like for every carbon, it's like there's a water that's there. So there's for every carbon, there's 2 hydrogens and 1 oxygen. So the sort of simplest ratio is where they came up with carbohydrate as that name. We are going to talk about the simple sugars, the mono and disaccharides, and we're going to talk more about the large polysaccharides like starches. We'll maybe get a chance to mention the medium ones. Those are not really big parts of your diet, but those are ones that are involved in the ABO blood group types. So the term saccharide means sugar. So that's where monosaccharide means that it is one, right? So mono tells you it's one single sugar unit. These sugars trigger the taste receptors and are sensed as something that is sweet. Carbon, hydrogen, oxygen. Remember in CHM, remember like the 4 main elements in the body. So you've got 3 out of the 4 that are here, carbon, hydrogen, oxygen. Disaccharides, the term di tells you that it is 2. So it's 2 monosaccharides linked together. In fact, we've talked about lactose when we talked about lactose intolerance back in chapter 5. And I told you that lactose is glucose and galactose linked together. And if you don't make the enzyme to break this, then it causes all of those issues when lactose gets into your large intestine. So that's an example of a disaccharide. So we'll go through the specific types. Monosaccharides get absorbed very easily. Disaccharides do have to get broken down in order to be absorbed. And then we have the poly. So the word poly means many. So polysaccharides, some like the polyunsaturated, they're like, oh, it's 2, 3, or 4. When we're talking about polysaccharides, though, we are talking about sugar molecule or carbohydrate molecules with 10 or more sugars all linked together in a chain. Okay, sometimes there's branches, sometimes they're just one long chain, but in reality, some of these can actually be thousands of sugars in size. So like one molecule of starch has like 5,000 glucoses, all linked into one really large molecule. So polysaccharides compared to the mono and disaccharides, these are huge in comparison. Size-wise, much larger than any of those simple sugars. And if you've ever put flour on your tongue, it tastes pasty. Okay, so flour is just kind of this pasty. It doesn't have a sweet taste. And that's because it's so big, it doesn't dissolve in your saliva, and it's actually too big to even fit into your taste cell. So your taste buds can't even detect it because of how big it is. So this is just sort of like a diagram that shows like a single sugar unit, 2 sugars, and we'll talk about this rings and what these rings mean as we progress through. So we're going to get into the monosaccharides. Characteristics of monosaccharides. So this first one that you see here, this is glucose. Glucose is the most abundant of all of the monosaccharides. Glucose, you know it is dextrose, or you know it is blood sugar. So when talking about somebody's blood sugar, it's referred to this way. You see that there are 6 carbons in it. So if you have a 6-carbon sugar, it is called a hexose, because hex means 6. So a hexose, so if I had 5 carbons, it would be a pentose. And those are really the 2 common ones. Sometimes there's 4, but we don't really talk about them. So I'm fine with just hexose and pentose as being the 2, and it's just telling you how many carbons in that sugar. The other thing that's interesting about glucose, do you notice that carbon 2, 3, 4, and 5, 6, that all of those have alcohol groups, OHs? So if you go down 2, 3, 4, they have OHs on specific sides to them. So they call them polyalcohols. Poly because they have a lot. And then basically every single every single carbon has an alcohol group except for that one special one at the very top. That is the double bond oxygen. So it's called a carbonyl group. But if it's on the end, remember looking at your functional groups, that is an aldehyde. So if there is a double bond oxygen on the end of the chain, and it's always going to be on the first carbon because that's how they would number it, it would be on that first carbon, then they know it's an aldehyde. So they would call this an aldohexose. So it is a sugar with 6 carbons with an aldehyde on carbon number 1. Because of all of these alcohols and oxygens, every carbon has an oxygen attached. Remember that oxygen is one of the electronegative atoms. So in this, that means that all those alcohol groups, they don't share their covalent bonds evenly. That means that you're going to get this slight positive and negativeness to the molecule. This makes all sugars polar. So when you put sugar in your coffee and stir it up, what happens? Do they separate or does it dissolve? It dissolves because it's polar like water. So having all those OHs, having that double bond oxygen as well, even though this is a relatively big molecule, because there's so many of them, it helps to create a polar molecule. So that is why sugars dissolve in water. So looking at these two, so notice that the OH groups on this left one is different than glucose. This is not glucose. Notice the OH on carbon 2 is on the right, 3 is on the right, 4 is on the right, 5 is on the right. So they're all on the right side. But it's still, if you count the number of carbons, 1, 2, 3, 4, 5, 6. So it is a hexose. And it's got that aldehyde on the first carbon. So this is the aldohexose. But then look at the sugar molecule next to it. How many carbons do you see? So that makes this a pentose, right? Because it's 5 carbons. So if you count 1, 2, 3, 4, 5, so it's a little shorter. And then if you look at where that double bond oxygen is, notice that it's not on the end. If it's not on the end, it'll always be on the second carbon. But if it's on the second carbon, remember that's a double bond oxygen in the middle of a chain. That makes this a ketone. So look at your functional group just to remind yourself what a ketone looks like. So they would call this a ketopentose. Just means that it is a chain of 5 carbons and that there's a ketone. It would always be on carbon number 2. So we'll talk about some of the different ones. But one last thing about sugars. is that sugars have chiral carbons. So you got to remember back to chapter 4 when we talked about a chiral carbon. Chiral carbons have two characteristics. One thing is it's a carbon with what? With 4 single bonds. So remember that carbon has got to have 4 single bonds, and every group connected is different. So that means this carbon would be, since it's got a double bond oxygen, it's not chiral. But this one, carbon number 2, to the left I have a hydrogen, to the right I have an alcohol group. So you see those are different? Yes? Okay. Above is that aldehyde group, and below is a 4-carbon group. So are all 4 of those different? Yeah, so that is chiral. But not only is carbon 2 chiral, carbon 3 is chiral, because I have a hydrogen on one side, I have the OH on the other side. Going up, I would have a 2-carbon group. Coming down, I would have a 3-carbon group, so that one's chiral. Carbon 4 is chiral. Carbon 5 is chiral. So all of those can create a non-superimposable mirror image. So if we look at glucose then, that one's just sort of showing you how you could pick out all those differences on every single carbon. They're different. So they said, well, we've got a name. We have to name the right and the left-handed form. So we have to come up with this naming procedure so that it's consistent, so that we know which mirror image form we're talking about. So D-glucose, the D is just referring to the position of the alcohol groups on that glucose. D-glucose is the form of glucose that you find as blood sugar, that you find in fruits, that you find in honey. It's all D-glucose. And in fact, most all carbohydrates that are found in nature, they're all D forms. So all sugars end up being D. So there's D-fructose, there's D-galactose, there's D-glucose. It's all that certain position of the alcohol groups on those chiral carbons. So you don't really see the L. This is the only one that I want you to be able to recognize. So if you look at D-glucose, so this is what they call the wedge and dash structure. So the wedges would be like showing like those side groups would be sticking forward if you were looking at each of those carbons. So in this one, carbon number 1 is the aldehyde, right? So you're seeing this. So you recognize, okay, this is an aldehyde. So I know that glucose has an aldehyde on the end. Carbon number 2 has an alcohol group on the right. Carbon number 3 has its alcohol group on the left. Carbon number 4 and 5 have their alcohol groups on the right. Carbon number 6, it doesn't matter because it's not chiral. Why is carbon 6 not chiral? Because it has 2 hydrogens. So remember that it can't have but 1 hydrogen. It has to have 4 different groups. So in this one, hydrogens to the left and the right. So it is not chiral. So typically it's just written out as CH2OH. They don't split it out because it's not a chiral carbon. So I remember looking at D-glucose. I just remember the alcohol, aldehyde on the top. Alcohol goes right, left, right, right. Okay, it's just the position of the alcohol on D-glucose. In fact, there's a lot of different combinations of mirror images that you can make from glucose. In fact, look at galactose. So here's D-glucose, just what we just did. But now here is galactose. When you look at it, do you see that it looks almost identical? There's an aldehyde on the top. Carbon number 2 has its alcohol group over on the right. Carbon number 3 has its alcohol group over on the left. Carbon number 4, what do you notice about that one? So they're different, okay? They're not in the same position. So that is what makes galactose different than glucose. Just the position of an alcohol group on one carbon makes it different than glucose. So there's actually a whole bunch, like talose is another example. And if you look at it, you can see that it doesn't, those alcohol groups do not match exactly what glucose has. There's like 16 different possible mirror image pairs that you could make. But this is the most common. So D-glucose is the most common one that you see. So let's talk a little bit about it, okay? Because being in healthcare, and this really doesn't matter if you're talking about 4-legged creatures or 2-legged creatures, you are going to see patients come in that have issues with glucose. So when they talk about your blood sugar, they are measuring the amount of sugar that's present in the blood. Blood sugar, also called dextrose, sometimes they call it grape sugar. Normal blood sugar is a range. So it doesn't have to be exactly something. It's a range. Anywhere from 60 to 110 is considered normal. So if you get up, check your blood sugar at 65, you're good. You get up, check your blood sugar, it's 105, you're still good. You're in that range, okay? Anything in there is considered normal. So where do you get sugar from? Well, you get sugar from all digested carbohydrates. So you get sugar from fruits, from vegetables, from corn syrup, artificial not artificial sweeteners, but like any kind of sweetener. You also get glucose if you eat starch, because starch does get digested into glucose, which then gets absorbed into the body. And so then it affects blood sugar. So glucose's primary job for the cell is to be used for energy. We can use fats. Remember when we talked about lipids, we said you can use fats for energy, but when you burn glucose, it's a combustion reaction. So if you take C6H12O6, so that's glucose, and you combine it with oxygen, it does take 6 oxygens, you can oxidize glucose and convert it to 6 carbon dioxides and 6 water molecules, and a lot of ATP. About 36 ATP from one glucose molecule. So in looking at this, do you see why this is simple for a cell to do? So you get glucose from all of your carbohydrate foods. Oxygen, how do you get oxygen to your cells? You just inhale, right? So oxygen diffuses into the blood and then it's carried to cells. So now cells have oxygen. So if cells make carbon dioxide, how do you get rid of that? You just exhale, right? Because that's also carried by the blood back to the lungs so it can diffuse. And then water. Water is a product, well, you're roughly 2/3 water. So the water just gets added into the cell water volume. It doesn't end up affecting the cell's function at all. So this is why they say that glucose is the preferred nutrient energy source, because all you need is oxygen. Oxygen, and you're going to make carbon dioxide and water, which are very easy to get rid of. So it's the preferred nutrient energy molecule for the cell. And all of your cells would really like to run off of glucose because it's super easy. And you can break that sugar down, make carbon dioxide and water and lots of ATP. But in order to be able to do this, you have to get glucose into the cell. Somebody that is a diabetic, they have difficulty getting glucose from the blood into the cells because there is a signal that they're missing. And that signal is a hormone called, what is the hormone called? Insulin. Okay? So somebody that's a diabetic, they either don't make enough insulin or their insulin doesn't work properly. So if we have low or no insulin, blood sugar comes in after you eat. No insulin, blood sugar just stays in the blood. Normally, when you eat, your pancreas secretes insulin. Insulin is the signal to cells. They open up and start to suck glucose out of the blood and into the cell, and they can then use it to make energy. If you don't have insulin, it's like you don't have a key to the house. Okay? You can have tons and tons of glucose outside of the cell, but without insulin, there's no way for that glucose to go into the cell. So there's 2 types. I will tell you that it is estimated that there is 110 million people in the United States alone that have one of these forms of diabetes. It's also estimated that about 40% of them do not know it, okay, because they have not been diagnosed. The first type is the one that really you're going to know. Type 1, they call it insulin-dependent diabetes mellitus. Insulin dependent because with this, somehow your pancreas is damaged. You were either born without a functioning insulin making cells in the pancreas, so your pancreas never made insulin, Or you may have had a virus as a child that actually destroyed the cells that make insulin. So something happened and your pancreas doesn't make insulin anymore. When you hit puberty, you go through massive growth, okay? Like my younger brother, he's 6'5". He's younger than me, but way not smaller. But he actually grew like 3 and 4 inches a year, like for like a 3-year, yes. He like used to complain that his knees hurt because of those growth plates. They were growing so fast. When you go through puberty, that increases cell activity. So if cells are going to be very active, what are they going to need? Energy, right? So if you don't have insulin, this is typically when type 1 diabetes shows up, because that energy demand cannot be matched because you don't have insulin. So the blood sugar out in the blood doesn't get into the cells. So what the cells say, we think we're starving. So cells, because they cannot get sugar, think they're starving, and they go to the other 2 nutrients to try and make energy. So remember, you have 3 nutrients. One we've talked about, so that's lipids or fats. So your body begins to burn fat. You also go to proteins. Where in your body do you have a large amount of protein stored? In your muscles. Okay, so what you start to notice with this person begins to lose weight because their body starts burning stored body fat, and they start getting weaker because they start to actually disassemble muscles. So the muscles begin to shrink and atrophy, all because they can't get glucose into the cell. So the cells are like, we're starving. In the meantime, these people are usually starving. These are the people that are eating constantly. So they are always hungry because these triggers, the brain's going, cells aren't getting any glucose. We really need to eat more. So these are people that are eating, but they don't put on weight. So they're eating, but they're actually getting smaller. What happens to all that sugar though? All that sugar ends up creating hyperglycemia. So hyper means what? Elevated, and glycemia is blood sugar. So this, when we're talking about hyperglycemia, this is if you're talking about numbers that are greater than 110 milligrams of glucose per deciliter of blood. Right? And if you did the banana lab with us, remember you did the dipsticks? Remember that was actually the unit those dipsticks was milligrams per deciliter. So if you did the banana lab on campus, then that's where those units come from. Most people don't talk about the units. They just say your blood sugar is 80 or your blood sugar is 40. They just talk about it, but it actually is referring to how much sugar dissolved in the blood. So hyperglycemia, along with burning fats and proteins, begins to create an issue. When you burn a lot of fat and protein, you don't just make carbon dioxide and water. When you burn a lot of protein, you end up with a lot of nitrogen that your kidneys have to get rid of. When you burn a lot of fat, you end up making what are called acids. So they are a byproduct. So proteins and fats are not as easy to break down. They end up creating stuff that your kidneys and your liver have to deal with. Carbohydrates, you make carbon dioxide and water. That one's pretty straightforward. But when you burn a lot of fats and proteins, then you're going to have these byproducts. If acid levels build up too high, then it can create what they call DKA. Have you ever seen a patient that was diagnosed with DKA? So that is diabetic ketoacidosis. So that's like the common short version that you will see written in a chart. And it means that they're diabetic and they've been burning a lot of fats and proteins, and now they have a lot of acids that are built up in the blood. If this happens, then blood pH can actually drop, which makes this person very sort of weak, tired, lethargic. Worst case, they can actually lose consciousness. They can go into a coma, and they can even die because of irreversible brain damage that can occur. So untreated type 1 diabetes can be life-threatening.
So I was diagnosed, my blood sugar was in the thousands, so that technically...
Yes. Yep, you are in that point. And a lot of times people think so people that have DKA, they may be even they almost may seem like they're on drugs or they're drunk or something, because it's really hard to think because your brain is just so overloaded because of this extreme acid as well as this excessive sugar. So they might even be slurry. They might be unsteady on their feet. They might just say, I'm just tired. And how many times have you had a teenager say, I'm tired? All the time. I'm so tired. And you're like, whatever. You don't know tired, girlfriend. You just wait. Wait till you have children. Then you'll know tired. But that's the thing. Sometimes it's missed. A lot of thirst, a lot of hunger. So they are eating and drinking a lot more than usual. But this extreme kind of listless, tired, I have no energy at all. I just want to lay here kind of sensation. Those can all be potential signs of type 1 diabetes, like actually getting to the point that you're seeing symptoms. The only way to treat this is you have to give them insulin.
Or if you're peeing a lot. If you're peeing a lot.
Well, because you're drinking constantly, right? So you end up having, and then there's glucose. You'll actually have sugar in your urine. There's so much sugar in the blood that your kidneys can't even filter it right. So it ends up having sugar in the urine. So it's another way that they can pick that up. So you've got to give them insulin. Giving them insulin, I said, is just like a key. So insulin tells the cells, go ahead, open up and take sugar into the cells and use that sugar for energy. So this is the only way that you can treat this. Unfortunately, if you don't manage this well, then over time, it is really the hyperglycemia that ends up causing problems. Because when your blood sugar, so you said your blood sugar was like 1,000? Anybody else had a patient? So I had somebody last night, she said she had a patient, the blood sugar was about 900. Should be between 60 and 110. So if you have a blood sugar of 900, that's almost 10 times more than it should be. So your blood is a little bit thicker than water. So just imagine dissolving all that sugar in the blood. It's more like maple syrup. So comparing water to maple syrup, which flows easier? Water, without a doubt. So if your blood is really thick, what is the pump for blood? Your heart. So your heart is having to really, really force to try and push this blood, just like if you think about trying to squeeze cold syrup on your pancakes. You know, you open it and you're like, okay? If it was water, it would just all fall out. But it's thick because of all the sugar that's in that syrup. So that's what happens to the blood. So this leads to heart disease. So the person's heart gets overworked, increases risk of having a heart attack, increases risk of having a stroke, because there can be so much pressure in the blood vessels that they just rupture. Also, little blood vessels that are called capillaries. Capillaries are the microscopic blood vessels. It's really where oxygen and carbon dioxide exchange occurs. Capillaries can't handle thick blood because the blood flows so slow that it just stops. And if it stops, then it clots. And if it clots, then that capillary bed shuts off. So now you start to lose circulation. So people that have long-term, poorly managed diabetes, oftentimes they describe their hands and feet as feeling numb. I don't even feel my hands and feet anymore. Okay. So nerves begin to die off. They call that neuropathy. Okay. So neuropathy is this loss of nerves, especially in the extremities. Also, poor circulation. You get a cut in your foot and you can't feel it. So then what ends up happening? Is it going to heal? No, because you have poor circulation. So circulation actually brings cells to try and repair damaged skin. So if you have poor circulation in the extremities and you get a cut, this cut just stays there, and that increases risk of infection, okay? And this is why people end up having to lose a toe, toes, foot, leg, okay? All because of this poor circulation. So really, hyperglycemia is kind of like the chronic damage that happens by poorly managed diabetes. But most of the time, it's that ketoacidosis when they're first diagnosed or they're not taking care of themselves, they're not taking their insulin like they should. That ends up like getting them into the hospital because they're found unconscious, because they're not responsive, because their blood sugar is 1,000, okay? But long term, the friends that I've got that are diabetic, the long term, that hyperglycemia really ends up causing problems because it just makes the blood vessels in the heart so much more damaged. Yes. Mm-hmm. Yep. So you can have a heart attack because the heart can't pump anymore. It gets so overtaxed that it ends up being damaged. You can also have a stroke because there's so much pressure in the walls of the blood vessels because the blood is so thick. Mm-hmm. The thicker blood puts more force on the walls, and that increases risk of stroke.
He's a diabetic, and he doesn't take care of himself at all, so now he can't feel his feet.
Mm-hmm. Is he type? So the second one is type 2. So it is estimated 90% of diabetic patients are type 2 diabetics. Type 2 diabetics, they may make some insulin, but the insulin they make doesn't work like it should. So this most of the time shows up in adulthood. You can see it in children, but it's more common. So they used to call this like adult onset. They used to call type 1 the juvenile diabetes. So that was usually because kids usually were diagnosed. You can have type 1 though. I had a friend who was like in her 40s was diagnosed with type 1 diabetes. Something just happened in her pancreas, just stopped making insulin altogether. But that's kind of unusual. Usually it's like younger. Puberty is when you start to see type 1. But type 2, this is when you have this change in adulthood. And what they have found is in many cases, it is very much connected to weight and body fat percentages. So if you have higher than normal body fat percentages, cells actually take away insulin receptors. So you might have insulin, but there's no lock to put the insulin in. And so what it's trying to do, it's your body's way of trying to burn more fat as a way of trying to counter that increase in body fat. It's still, though, it's usually not like life-threatening. They don't usually end up in ketoacidosis, but they do have periods of hyperglycemia. So hyperglycemia is really the big problem with type 2 because that leads to neuropathy. So think of neuropathy as this numbness in the extremities. It leads to heart disease because of the periods of time when your blood is too thick and your heart was working so hard. It leads to this poor healing. So when you do end up having kind of injuries, surgeries, whatever, you're not going to heal as well. And in fact, hyperglycemia can lead to kidney failure. So this can actually cause damage to the filters in the kidneys so that the person has to go on dialysis. So that's really like the number one reason that people are in dialysis centers is because of diabetes. So treatment for this, there are medications. So they oftentimes try to get things under control. But a lot of this has to do with diet too. So decreasing carbohydrate intake, if you eat like a low carb, and I'm not saying that you have to do the whole hardcore keto diet type of thing, but decreasing carbohydrate means what's going to happen to your blood sugar. It's just not going to go up as fast, okay? If you have like the chips and the bread and the potatoes, your blood sugar is going to spike. And if you don't have insulin on board, it's going to stay higher than it should. But if you stick to some of the lower carb, more vegetables and meat and healthy fat type of diet, then you'll see not as much of a shift or change in blood sugar. And that requires like less medication. Because some of those medications actually have some really negative side effects. Like they just make you feel tired and crappy. So that's typically type 1, but there are some type 2 diabetics that because they don't check their blood sugar as often, and I'm sure you've probably seen it. So it looks kind of like this little white piece, little white disc, because it is like band-aided. It's like adhered to the back of someone's arm, or you can put it really anywhere on the skin. They like to put it someplace that it's easily to access because it actually constantly monitors blood sugar. And all you have to do is take your phone and hold it next to it, and it like Bluetooths the information so that you know if your blood sugar is 120, or you know if your blood sugar is only 50. So that can help you to decide, I'm going to need to eat some carbohydrates because my blood sugar is only 50, okay? Or I don't want to. I might actually have to take some insulin if my blood sugar is 180. I may need to try and get it down because just think, anytime that blood sugar is not between that 60 and 110, that's when you end up with problems. Mm-hmm. And there are some people, like in the type 1 especially, there are some people that have what they call brittle blood sugar. So like just eating like a bowl of cereal will cause their blood sugar to go up into the 200s. Like most people, that's not the case. But for them, it's such a dramatic change. Like their blood sugar goes way up, then it comes way down. Then it goes way up, then it goes way down. So they have periods of hyperglycemia and then hypoglycemia. And so to try and keep that balance, that's where an insulin pump comes in and is very helpful. So one way that they can diagnose you is they can look at what's called A1C. So A1C is actually looking at a 3-month rolling average of your blood sugar. So here's what we used to do. When I knew people that like were borderline diabetics, like they were like, I have to go to the doctor next week. So for like a week, they would like eat salads. No, I'm not going to have those cookies. No, I'm not going to have that cake. No donut. Not going to put sugar in my tea. And then they would go to the doctor and they were like, oh, your blood sugar is only 80. And you're like, great. And then you leave and you're like, calm, right? Okay. So they're still having periods of hyperglycemia. But if you go and just pull a blood sugar, that is literally just a window of what your blood sugar is right now. So that wasn't as helpful. A1C is what your blood sugar average has been over 3 months. You can't cheat. Okay, so if you've been eating a lot of sweets, a lot of high carbohydrate foods, it's going to show up. And in fact, normal should be less than 5.7. When you're at that 5.7 to 6.4% in your A1C values, they say that you have pre-diabetes. That's telling you you have had periods of hyperglycemia. Over the last 3 months, you haven't been in hyperglycemia a lot, but you have had periods of that, and any periods of hyperglycemia is going to create neuropathy, heart condition. So if you've already got like hypertension, you're just making all of that worse. So that is where A1C really has helped kind of like identify patients that are kind of going that route, because changing diet, trying to change the amount of exercise that they get. They have shown that exercise helps to improve receptor numbers on body cells. So trying to get exercise on a daily basis, they say now like sitting at your job is the new smoking. That was like one of the new things they've been saying. So if you live a sedentary life, then you're not burning those sugars. Sugars that you're taking in are not getting used for muscle contraction. So where does that go? Does it create this hyperglycemia? Is it getting stored as fat? Okay, but you are all like, even if you're taking care of 4-legged animals, like I know people that have diabetic dogs and cats. Okay, so they end up having to titrate their insulin levels. They have to control their food. They have to give them insulin daily and try to monitor that to see if it's like keeping it within that normal level, because otherwise that animal is going to end up having a shorter than normal lifespan. So whether you're talking about people or animals, same thing. And it is one that's kind of a pretty common one now that you see. These poor little old chubby dogs coming in. And it's not always that they're chubby. Well, a lot of times they're a little on the overweight side. And that's like the part that you see with that type 2, that it ends up causing those issues. All right. All right. So I'm going to quit there. We will talk about the other sugars. So we're going to talk about galactose. We're going to talk about fructose. And then we're going to talk about the polysaccharides. We're going to talk about starch, fiber, and glycogen. We should be able to finish this lecture on Thursday.